So now we move to the second talk of the day. It's going to be by Umberto Tarantino, and the title of the talk is Ultracategories via Kan extensions of relative monads. Umberto, you can take the stage.
Thank you, Ivan. Thank you for inviting me. Thank you to all the organization for having me. I will report on some joint work with Joshua Wrigley, who's a postdoc at UIF, where I'm a PhD student. And just a bit of a disclaimer, if you were there at CT, this will be essentially on the same material. So apologies for the repetition. But okay, so the starting point of the story that I want to talk about today is the category of compact outer spaces. And the idea is, among other things, there are two particular properties that we will care about in this talk of the category of compact outer spaces, which is they are algebras. They're algebras for the ultrafilter monad on set. And the functor, or we will focus on the functor, but actually the whole monad is induced in a universal manner, in this case, from the inclusion of finite sets into sets by means of right-Kan extension. This is very well known. Probably something which is slightly less known, but also quite famous by now, is that every monad, in this case on set, can be represented instead of the usual unit and multiplication form in a no iteration form. This means that we can specify the monad by choosing a function, which will act as a unit for each set, and an extension function, which tells us how to extend functions over beta of something to like along the unit, let's say. Indeed, I'm not going to write the equations here, but you can imagine, for example, that extending and then precomposing with the appropriate unit gives back the function that we started with. And if you think about this topologically, if you think about the usual topology on the space of ultrafilters on a set, this is basically the function telling us given a set function, so just a function from y to beta x, the unique extension which is continuous from beta y to beta x. And in the same presentation, we can also speak about algebras. And so now the datum of a beta algebra K is given by an extension operator for maps for functions over K. Also, again, satisfying equations. And the idea here is that if we have a functions from h from y to k, well, the extension at an ultrafilter nu, in this case, is a sort of topological limit of the sequence of points represented by h, computed with respect to the ultrafilter nu. So in a sense, along a direction specified by nu, a way of convergence specified by nu. And this is kind of the idea that we will take in the rest of the talk to speak of ultra categories. So this is the only logical slide with less with more logical content. Let's say ultra categories were introduced by Makkai as a way to categorify the notion of ultra products from model theory. So intuitively, there are many different definitions, most notably the one by Lurie, which is a great simplification of the one given by Makkai. But in all definitions, there's this idea of a category with some extension functors, which in a sense compute ultra products in the category. And the shape is the same one that we've just seen for compact algebras, for beta algebras. So we lift functors now from a set Y to C, where Y is seen as a discrete category, to beta Y, also seen as a discrete category, over C. This datum was called pre-ultra category by Makkai. And now the topological limit that we had in the beta algebra case represents the ultra product, in a sense, of a family of objects indexed by H with respect to a choice of ultrafilter nu. And the key example of this whole framework, let's say this whole theory, is the category of models of a first order theory. I wrote coherent here, but you can just think about a first order theory, where now the abstract ultra products given by this extension functors are just actual ultra products of models. So the question that started this bit of research that I'm talking about today is, can we make an axiomatization of ultra category emerge as compact algebra spaces emerge. So as an algebra for some kind of monad now on categories, and maybe possibly in such a way that at least the functor, but maybe also the monad, is induced in some universal way from the ultrafilter monad itself. And this idea ties with some remarks in the literature already present, and I'm quoting here, a remark by Ivan, the choice of axioms that define ultracategories in Makkai, but also in Lurie, it works to obtain the theorems that we care about in the theory of ultracategories, but it feels quite arbitrary, and it is also very heavy. But there's also this other quote by Tom Lancer that I want to mention, which is ultra products are categorically inevitable, as in they emerge universally just by the inclusion of finite sets into sets. So can we make ultra categories emerge also in a categorically inevitable way? And there are also previous approaches to this problem in the literature, mostly focused on making Makkai's ultra categories emerge as algebras, making Lurie's ultra categories emerge as algebras for appropriate monads. So it's like the same idea, but not exactly the same point of view that we chose to have. And in particular, I'm mentioning here Marmolejo, Rosolini, and Hamad, referring respectively to Makkai's ultra categories and then Lurie's. What we will do instead is the starting point of this was the observation that Lurie's ultra categories are almost exactly algebras of some kind for a relative monad, for a relative two monad over cat, in this case, locally small categories. So we will use and generalize some tools from relative monad theory to address this issue. So let me start by just reminding, if you haven't seen it, the notion of that we will work with. So the notion of a J-relative two monad on cat. So if we fix a two functor from some two category into cat, a J-relative two monad is given by choosing an object for each a category for each object in our base two category, a functor from JB into this category, which will act as a unit, and then an extension functor from functor JB to TB primed over to TB primed. So again, this will tell us how to extend functors along the unit. And indeed, the axioms are exactly saying essentially how this extension should behave with respect to units and with respect to compositions, let's say. The main example, you could say, well, okay, this is very specific in a sense, yes. But also, if we choose some J which is twofoldly faithful, for example, the inclusions of sets into cat as discrete categories, then every two monad on the base two category canonically induces a J-relative two monad just by composition, which means that every monad on set, for example, can give us a relative two monad in this sense. And in particular, the one that we will care about is the relative ultrafilter two monad, which is just composing the ultrafilter monad with the inclusion into cat. So, okay, we define weak ultracategories to be Colac algebras for this relative monad. Let me spell out what this means. Well, it's a category with an extension functor, again, of this type, a natural transformation which will act as a uniter for the algebra, and then for every other function over the extended domain, we can also extend it according to the laws of the actual monad, so just in set. And then we have a Colak's associator, let's say, relating the two possible extensions that we have in this diagram. I will spare you the coherence conditions, but the crucial point is that this notion is slightly weaker than Lurie's one. It's almost exactly Lurie's one, but he requires every uniter and some associators to be invertible. But the point, which makes the theory works in a sense, is that the notions of morphisms between ultracategories that Lurie considers coincide with the notions that we get from like the algebraic point of view. And I'm not going to go into too much detail about this, but the idea is to obtain the main theorems of the theory of ultracategories, we just need some we can just have a fully faithful extension of Lurie's notion, for example, and then they will carry on for our notion. So yeah, ultrafunctors are pseudomorphisms of Colac algebras, and left ultrafunctors that Lurie considers are Colac morphisms of Colac algebras. Now the idea is, if we want to realize weak ultracategories as some kind of algebras for some kind of monad, an actual monad now on cat, not a relative one, well, okay, the main observation here is that these extension functors assemble into a lax transformation, which, if you need a refresher, is just a kind of natural transformation where instead of having naturality squares commute on the nose, we have some coherent two cells going in one direction, filling the squares. If we want to express weak ultracategories as algebras for a monad on cat, then these lax transformations need to correspond, in a sense, to functors from some category built from C into C. Indeed, the algebra map. So, okay, we just define in abstract, in full generality, given two functors J and T parallel from some two category B to some two category A, we say that T tilde is a left Oplex-Can extension of T along J, if it exists. If it is a two functor from A to A now, with this isomorphism, with this family of natural isomorphisms here, so that lax transformation of the appropriate kind correspond to one cells in A of the appropriate kind. If you instantiate A to be a cat, this collapses to what we had here. And if this notion of Can extension is a bit maybe surprising for some of you, there's a more familiar one that we can extract from this, because if it exists, T tilde comes equipped with an Oplex transformation zeta here from T to T tilde J, which is universal in the sense that every other Oplex transformation of this kind here uniquely factorizes through zeta by means of a strict transformation from T tilde. So this is maybe the more familiar notion of Can extension in the one-dimensional case, or close enough. And this means that we have this family of isomorphisms here, isomorphism categories here, which means that we have a two-adjunction between taking left Oplex Can extensions and precomposing with J, modulo considering the appropriate notion of transformation. In the one-dimensional case, this is not weird at all. Indeed, if you allow me to restate for a second what is in the Altenkirch, Chapman and Uustalu paper on relative monad theory in the one dimension, the idea is there fix some functor from B to A. Left Can extensions, of course, they determine an adjunction from functors A to A and functors B to A, where the right adjoint is precomposition with J. And we can transport the monoidal structure of functors A to A to the other category on the right, which gives us a left skew-monoidal structure. And the product, the composition, the tensor product, if you want, is given by taking the Can extension of the left one and composing with the right one, or precomposing if you want. And then what they do in the paper is that they show how J-relative monads coincide with monoids in this skew-monoidal structure. And then under some appropriate hypotheses, this category is actual monoidal category. And in parallel, the functor taking left Can extensions is monoidal as well, in the sense that it sends monoids to monoids, which means that, well, relative monads, monoids in BA, can be unrelativized by taking left Can extensions, as in they get sent to monoids in 8A. What happens in dimension 2, or at least in the setting that we care about? Okay, fixing now a two functor as earlier, left Oplex Can extensions determine a two adjunction, sure, if they exist, of course. And indeed, with the same definition, we get that the category of Oplex, two functors and Oplex transformations from B to A is a left skew-monoidal 2 category. Sure. And J relative 2 monads are now a kind of monoid inside the skew-monoidal category. But what about the fourth point here? Well, in principle, yes, if we find sufficient hypotheses which make this structure monoidal, then in parallel, taking left Oplex scan extensions will be a monoidal functor, let's say pseudo-functor, and it will map monoids into monoids. But the crucial point is that in the case of the inclusion that we care about, so sets into cat, well, it's not monoidal. So what do we do? The theorem, the sweet spot we found to solve this issue in a sense is given by our main theorem in the paper, which is saying if we have a J relative 2 monad on cat where J is 2 fully faithful, B has a terminal object and J preserves it, and B has at least every Oplex colimit of shape JB op for B in B, and J preserves them, then we can perform this unrelativization by taking left Oplex scan extensions. So this means the left Oplex scan extension of T carries the structure of a pseudomonad with the same 2 category of Colax algebras. And crucially, these assumptions are not enough to make the skew-monoidal structure a monoidal structure. And also, as you can see, compared to maybe a more direct approach to finding an algebraic presentation of ultracategories, this theorem is in principle a lot more general. Okay, in case of cat, here there's some size conditions to take a bit of care on. But let's say that in the case of B, the base 2 category being set, we can also assume that cat is the 2 category of locally small categories. And well, then left Oplex scan extensions exist, and we can describe them explicitly. I will just describe the case of beta, which is the one that we care about in this talk. So the idea is, given a category C, beta tilde now of C is the category of formal ultra products of tuples in C, which means they're just given, like its objects are given by a set, a functor choosing an object for every element of this set, and an ultrafilter on this set. So in a sense, they're indexed families of object with an ultrafilter on the set. Morphisms from such a triple to another are given by functions between the index sets going backwards and preserving the chosen ultrafilter, together with the natural transformation filling the obvious triangle. And if you're aware of, for example, if you were there for Rosolini's talk at CT24, you might be surprised to see that there's no quotient on these morphisms, as in we're not identifying functions which agree on a big subset according to the chosen ultrafilter. And that's essentially the only difference compared to the pseudomonad that was defined by Rosolini and then also used by Hamad to prove that its Colax normal algebras are Lurie's ultracategories. So if we have, the idea is that if we have a weak ultracategory C, then we have the extension functors that I talked about in the beginning, and then the corresponding algebra map will just map a formal ultra product into the actual ultra product computed according to the extension functors. So this will be, intuitively, this will be the way that we make Colax algebras of the relative monad correspond to Colax algebras of the extension. I will now give a bit of, I will construct the actual pseudomonad structure on beta tilde if I have, because in the case of beta, of course, the hypotheses just are satisfied on the inclusion because, of course, the inclusion of sets into cat is fully faithful. It preserves the terminal object, and it preserves small coproducts, which in particular exist in set. So we can define concretely the structure of a pseudomonad on beta tilde, where, okay, on objects, the unit is simply mapping each object of C to the singleton of C with the unique ultrafilter on the one element set. The multiplication is slightly harder to describe, but the idea is sort of easy enough because if we have such an object, a triple in beta tilde squared of C, well then for every x in X, H gives us a triple again. So we introduce some notation here. And the idea is simply we take the coproduct of the first components, we take the coproduct map, the choice of all the objects given by H, of all the objects of C given by H, and then we compose all of the ultrafilters that H gives us according to the ultrafilter nu. So it's just this Q star of nu here is simply the ultrafilter on Y, the coproduct, which accepts a set S if and only if a new big subset of theta x's accept the pullback of S along the inclusion. So the component of S inside each piece of the coproduct. But this, I presented it in this for beta, but all of these considerations are only, let's say, monadic in the sense that this general structure of the description is exactly the same that works for every monad that we are extending. So what we get in the end is this diagram, essentially. So we can conclude that weak ultracategories are a category of Colak's algebras for a pseudomonad on categories. And in particular, the pseudomonad is the left topological extension of beta, seen as a functor from set to cat, along the inclusion of sets into cats. But then, okay, I will just conclude with some future direction. Maybe I went a bit fast, but I will conclude on a couple of future directions of work, because as I said, our result is general enough that it can be applied to, in principle, at least to any other monad on set, but also on other categories which embed into set. For example, posets. If we take the upper prime filter monad, which means the one that has compact order spaces as its algebras, well, we have a notion of Colak's algebras for the relative upper prime filter monad, which we can unrelativize and prove that it's exactly the same. It's algebraic over cat in a Colak's sense. And we get something which we momentarily call prime categories as its algebras indeed. So the idea is, can we do something analogous as what happens in the ultra category world for prime categories? Can we prove something for positive model theory, which is how let's say coherent logic is called in the model theory world? Can we do some kind of Priestley duality instead of stone duality for first order logic? And then another direction in a more categorical sense is, can we abstract our unrelativization procedure to just a theorem about two functors between two categories, or maybe pseudo functors between bicategories, whatever, to have an abstract unrelativization procedure? Because for now, we really need the codomain two category to be cat for the process work and to go through. But yeah, and that's essentially all I wanted to say. Thank you.
Thank you, Umberto, for your talk. And now we move to question time. We have time for some questions, absolutely. So if someone wants to ask a question, please unmute yourself and speak. Oh, Walter wants to ask a question.
Yes, first of all, thank you for your nice talk. So the ultrafilter monad on set, there's this remarkable property that it's really a property of the endofunctor, because the monad structure is uniquely determined by Berger's theorem. So I wonder whether anything like this is imaginable for your extension to the pseudomonad beta tilde on cat.
You mean something like the fact that it preserves finite coproducts, like in that
Yes,
sense?
I mean, because of this fact, you just need the endofunctor and the rest of the monad structure comes by itself, right?
Okay. Well, in that sense, yes, as in, I don't know if I can say that it's unique in any sense, but it's uniquely determined, let's say. But even if in the talk I focus on the actual functor, the rest of the structure is also sort of canonically induced by the fact that it is a left oplex scan extension. So we can just drive the yeah, it is determined in a sense. I don't know if it's determined universally. I've tried to think about some characterization in terms of, preserving something. It's the unique monad, whatever. I couldn't find anything yet.
Okay. Oh, thank you.
Thank you.
So I will use my power to make a comment on this. The codensity monad of a full subcategory has only one unique structure of monad on it. This is a classical result.
Yeah.
So I would expect that as long as you do codensity monads of full sub stuff, then the structure will be unique. And the proof should be the same, which is actually a trick. It's not a very creative proof in a way.
But you mean it will, like, the uniqueness will carry over to the extension, because this is a left kind of extension. So
That is true. That is true. But it will be at the end of the day a codensity monad, right? So this is what in my paper I call generically idempotent monads, and I think the monad structure should be unique on these objects.
Okay. Thank you for the remark.
Do we have other questions though?
I don't understand why it's a codensity monad, this beta tilde. Why you say that? Because I think, as Umberto said, with the left and right, something goes wrong.
I'm very happy to be wrong. I could be, absolutely.
Me too.
You mean you're very happy that I'm wrong? I get that.
No, for myself to be wrong.
Well, I would say Berger's original theorem is more than a trick, right? I mean, as far as I remember, Garner in his paper of maybe 2020 or so, he has a nice proof of it, but it's definitely more than a trick, right?
But I think we are mentioning different observation because I think yours is the preservation of coproducts, right?
Right.
What I'm mentioning
No,
is
I understand. Sorry, yes.